Hello and welcome back. My name is Ian and today we'll be looking at a TMB temperature module. We will be looking at how to read the serial data from it using an Arduino Mega. Now arguably this project has been 30 years in the making, but that's only because the thing's been sitting on my shelf for that long. In reality, I've only been working on this for a couple of weeks. Anyway, let's have a look at some of the hardware we're going to be playing with. So, what you can see here is an awful lot of stuff that's nothing to do with what we're looking at today. We can forget about that, we can forget about that. What we are interested in is this. This is the TMB module, or to be precise, it's the MB-TMB880CF-1 module. So as you can see, it sits and reads the temperature. It does other things as well, apparently, if you connect switches and stuff to this. This is the interface connector on it. You can see, well, probably you can't. What you can possibly make out is there's a few wires connected to it. I've got a ground, and then we've got pins 9 and 10. So 3 lines going over, and then 3 lines going in to my Mega. We've got some lines coming out of the Mega. We'll be looking at those on the scope later. They're the reconstructed pulses. Now, talking of pulses, have a look at this. So what you can see is pins 9 and 10 give us the data. 9 is the data, 10 is the clock. You can see it's only got an AA battery in here, so the data and the clock are 1.5 volts peak to peak maximum. As it happens with this battery, because it's not brand new, it turned out for me it was 1.35 volts peak to peak maximum. Anyway, you can see that the clock pulses tell you, it's the falling edge of the clock pulse that tells you when you can read the data. And if you've got good eyes and you can see the clock pulses, you'll see the first one is a little bit bigger than the other. Well, all the others. All the data sheet tells you is that the subsequent clock pulses are 125 microseconds long, and all you can tell from the drawing is the first one is bigger. Didn't tell you how big. As it turned out for me, it was about 975 microseconds, give or take. Anyway, being 1.5 volts gave me the first problem. How do I read that in? I was looking and thinking about level sensors, level converters. The research led me on to comparators, and then that led me on to the fact that there's a comparator built into my Mega. It's built into all the Arduinos. It's just the one comparator, and using that I have been able to read the clock. So comparator really does compare two voltages. In this particular case, one of the voltages is held at a reference, and then all it does is tell me whether the other line, i.e. the clock, is higher or lower than the reference. The reference in this case is 1.1 volts, my maximum is 1.35, perfect. Another good thing about the comparator is that it can generate a hardware interrupt for you. So I can wait until I've got a pulse from the comparator and then do something with it. The something is to read in the data. Now, it's also 1.35 volts peak to peak, but I'll just read that in with an analog to digital line. Arduino's got lots, so I've used one. Anyway, let's look at some code. So, what have we got here? Well, we've got a small script, a sketch, as they're called in Arduino speak. I'm dipping into Python mode. Never mind. So what are we doing in this? What are we doing in this sketch? Well, actually, we don't do very much. Let's include a library. This is actually dealing with the comparator and using it isn't actually too difficult to do it on its own. But I like using libraries. The abstraction is it's good for me. It works. So using the library, we'll get to some calls that we make off this library in a bit. Set up some of my pins. The clock is going in on pin 5. It's digital input 5. That is the known as the AIN1 line when you're using the comparator. The other line, the AIN0 line, is not even presented to a pin in the Mega. It's presented to a pin on the Arduino Uno, I believe, and the Nano. But my Uno and Nano are busy. But as it happens, I don't need it to be presented to a pin because you can connect it to the reference voltage, and that works fine for me. Then I read in my data. This is the data pin on A5. 5 and 5 worked for me. Built-in LED, I'm not doing anything with it other than turning it off. I found that for some reason it was always on my Mega, and that annoyed me. Then I'm reproducing the clock and the data out on pins 9 and 10. They're going to an oscilloscope. We'll look at that later on. So, what am I doing? I'm setting up some global variables. These things are updated by an interrupt, which we'll get to in a bit. And interrupts, you can't pass variables to or from them, so it's globals is the way to do it. So I've got a global flag that tells me whether it's detected a new pulse, and that's when I will then read the data. This actually will get set to true when I've got a falling edge. Another thing I'm doing is I'm setting up a big variable, an unsigned long. That's for me to measure the width of the pulses so that I know when I find the first one and can start my bit count to read in the rest of the bits. I'll be using the micros command. That's a friend of the millis command, but it measures micros and not milliseconds. Means it trips over after about 70 minutes, I believe, but that's neither here nor there for this. Right, into the setup. This is me sorting out that LED that's always on and annoyed me. Then I set up my in and my out, and then this is where I'm using that library. I'm setting up my comparator. I'm telling it I want AIN0 to be the internal reference, and I want AIN1 to be used as in real pin AIN1, which happens to be digital pin 5 in the Mega. I then want an interrupt. I'm telling it this is my interrupt routine. We'll look at that in a bit. And I'm telling it I want to call this ISR interrupt service routine. I want to call it on changes. That means rising and falling edges. And that's because I need to know when the start and the end of a pulse is so that I can measure it. Into the loop. Let's have a look at the loop. Got some things that count in my bits. And then when I've got the bits, I work out a temperature. We'll see that in a moment. If I've got a pulse, I'm checking to see whether it's a larger pulse. As I said earlier, most of the pulses are the small ones. Then the big one is the first one. Small ones are 125 microseconds. The big one is bigger. I found 975, so I'm just looking at it. If it's greater than twice the size of a normal pulse, I'll treat it as the first one. That's been rock solid. If it is, I reset my bit counter to 0. The first bit in the stream is the sine. So there's 13 bits in the stream. I haven't told you that yet. Yeah, there's 13 bits in the stream. The first bit is the sine bit when you're in centigrade mode, which this thing is by default unless you set one of the other pins. So the first bit's the sine bit, and then the remaining 12 bits are the 3 digits of the temperature, 4 bits per digit. You get the tens, the units, and then the tenths. The 4 bits are binary coded decimal, so we'll see a BCD conversion later on. I then print out something. I want to see the pulse width, so you'll see that in a bit as well. And then, assuming we're not on the last bit, we'll increase our bit counter. If we're reading in the first 12 bits, this is what it's doing. When it reads in, because I've got 12 bits, I have to read it in a bunch of 8 and a bunch of 4. Because 8 bits in a byte, and I've got 2 bytes, I need 1.5 bytes for this stuff. So I read in the first 8 bits into this variable, 1 bit at a time, and then I read in the last 4 bits into this variable, 1 bit at a time. This reads in 8 bits, and this one reads in 4 bits. I also print out my pulse widths. You'll see that in a bit. If it's the last bit, as in we've got the 12th one, the 12th bit, we take all those bits we've read in and we convert them from BCD into a float for the temperature, and then we print it. And then this is just tidying up the output pulse. You'll see that later in the scope. So there we go. The BCD, not too difficult there. The only clever bit had to be putting a float in here, because this is actually the fractional part of the temperature in centigrade, the 0.1 or 0.2 or whatever. So we need to put it into float, otherwise our integer maths just takes it away. It all becomes 0. I found that out the hard way. Right, so let's have a look at our two routines. As we've been calling the data in, this is the data in routine. This reads in a bit for me, and that reads in a bit once I've been given a pulse indication. The pulse indication comes from the clock pulse ISR, which is the thing we set up on the comparator output. First thing I do is I get the value of that comparator, because I need it later on to know whether we've got a high or a low. Because of the way this comparator works, you have to invert it. The comparator gives me a hard 1 whenever the input's a 0, because of the way it's working. You can read that up. Some of the references at the top of the sketch will give you the clues for that. So anyway, there's the bit, the actual clock pulse, the value of it being read in. I read it. What am I doing? That's reading in the value of it. This is reading in this is actually not reading in at all. This is writing out. This is my output to my pins 9 and 10 for the scope later on. If I've read a 1, that's the start of my pulse. If I've read a 0, it's the end of my pulse. Therefore, I can work out the pulse width and tell the main loop that we've got a pulse. When we have told the main loop we've got a pulse, this is what it calls. This is just reading in an analog pin. I know that my volt's going to be 1 point something, which means it's going to be greater than 200 once it's been through the ADC. So if it's greater than 200, I know I've got a high, otherwise I've got a low, and that's what I return, high or low, and I write out what the value is to one of those other pins for the oscilloscope. Anyway, that's all the code looked at. Not a lot going on with it. If we have a look at the scope now and see what we've got. So let's move down to the scopes view. Hello, this is future me adding in a little bit. Whilst reviewing the footage, I realized I forgot to show you something. Specifically, I forgot to show you the output from the code. So every 10 seconds it's printing something. It's currently saying 23.4. If I look at the thing, is 23.4. So that's all I wanted to add. This is the serial output, and the temperature decoded from the BCD. Anyway, I'll let you go back to me in the past. Bye bye. Oscilloscope. There we go. So this is on single trigger. You could see from a previous triggering, we've got the red trace, which is my clock, and you see the wider first pulse followed by the series of, well, there's 12 of those thinner pulses. There's 13 pulses in total because there's 13 bits of data. And then the blue trace is the data itself as per the pulses. In this particular case, it's telling me that the blue data is telling me, so here is a 0. Well, that means it's positive. Okay. Then we've got 8, 4, 2, and a 1. So that's a 2. When you look at the BCD, that's 2. So this is the 10, so that's 20 something. Got 20 something degrees centigrade. Then 8, 4, 2, 1. That'll be 22. And then we'll have 8, 4, 2, 1. I've got out of step, haven't I? 8, 4, 2, 1, 8, 4. So that's 24. 2, 1, 8, 4, 2 and a 1. 2 and a 1 makes 3, so that would be telling me it's 24.3. Let's capture another one. So we'll wait for it. There's an output from this little unit every 10 seconds. And there we go. And there's another one. So what temperature have we read here? We have read positive again. 8421, so it's 20 something again. 84, it's 24 again, 2 and a 1, and then it's 84, 2 and a 1, so it's 4, 5, 6, 7, so it's 24.7 according to this. And if I show you the temperature, 24.7, we have a winner. Excellent. If I breathe on this, we'll hopefully get the temperature to change. Yes, it has changed. And if we do another capture, so what's this? Currently the temperature is reading 27. No, it's changed, 25.6. I didn't breathe long enough. So that's positive 842, so there's my 20. And then we have our 8421, so that's our 25. And then 842, 4 and 2, 6, that's our 25.6. That's where it all comes from. So there we have it. That's what I've been doing. I'm very pleased with the comparator. Using those as a level converter was a bit of an education for me. I quite enjoyed that. Anyway, I hope you found this video useful. All the code and data sheets and stuff like that, everything referred to is on GitHub, and the link will be down below. If you like this, please tell me so. Otherwise, I'll see you on the next one. Thank you very much.